The general title of my presentation is Symmetry in Design and Analysis of Spatial Structures. After reviewing of all results of my research and professional activity, I came to the conclusion that the consideration of the basic rules of symmetry together with application of principle of superposition have always been present during the design processes carried out by myself in the field of shaping and analysis of various types of the spatial structures. In one of my first projects, I proposed a spherical form of the crystal space frame as the support structure of the dome, having an interesting exterior architectonic view and at the same time having an advantageous conditions of the daylighting of its inner space. 3 decades ago, the process of preparing a series of similar technical drawings took me several weeks. During this work, I studied morphological aspects of a very modern at this time structural system of the cable dome proposed by David Geiger. From this time, I had an idea how to design a similar system based on suitable transformation of spherical form of the just spoken space frame. Simplified scheme of the transformation is shown on the left-hand side of the slide. Because during the technical drawings take a lot of time, I have postponed the presentation of this structural idea until the time when I will be able to use an efficient computer-aided tool. As a result of my cooperation with the Space Structure Research Center at the University of Surrey, I have had an opportunity to study and to learn principles of the Formex algebra and the programming language Formian, invented by Professor Hoshiyar Noshin and then developed also by his team. My ability to practical application of various functions of Formian has enormously enriched and accelerated my research and professional activity. This slide shows visualization of a numerical model of the same dome structure defined in Formian. Result of the mentioned transformations is shown on this drawing, presenting the basic shape of the crystal tension structure. This system, like the Geiger's cable dome, can be a structure of the dome cover of very large clear span and having very small rise, even equal to 0, which is considered as an advantage of such structures. The structural arrangement of components of this system was subjected to the further transformations, resulting in numerous new types of the dome tension structures. An example of one of them is shown on this slide. Tetrahedral modules are the important part of the structural system interspaces of a large group of these systems. The denotation of the structure is quite complicated, but I have chosen such system of denotations in order to reflect in their names the morphological order of each system. The spatial structure is also built of the tetrahedral modules spaced and alternately located over every second lower triangular area of the funicular truss and suitably connected together, as well as to the compression perimeter ring. The next group of such systems is created by application of the doubled form of the spatial hoops, and one example of it is presented on the slide. The vertex of the tetrahedral modules are joined together by the relatively long cables, and together with other tensile members, they create a huge double form of the concentric hoop. The huge double spatial hoops can be multiplied inside the inner area of the cover, like it is shown in this drawing. Due to the previously mentioned reasons, it can be the bearing structure of the roof cover having a huge clear span. The next group of structural systems is shaped by usage of the same type of the tetrahedron modules, arranged this time above and below the triangular hexagonal grid composed of struts located in the middle layer of the created spatial structure. Vertex nodes of these tetrahedrons can be connected in various ways. In my opinion, the structure VATH number 2 has a great development potential because the suitable arrangement of, for instance, the membrane sheets will give a very interesting architectonic form to the roof structure. That is why I propose the spherical geodesic shape of this system as the support structure of the central building of the previously designed new campus of my alma mater university. In the conceptual design, the building was intended as the testing object to carry out the long-term strength research and also testing of various types of the cladding systems. Support structures of the tall buildings can be also accounted to the wide family of the spatial structures. So far, I have proposed two types of the foundation structures. The structural concept of the final shape of the system, or of the system of composite foundation, is presented in the next slide. The point of the proposed technical solution is as follows. In a narrow space between two horizontally located beams is arranged an intermediate structural system which is connected to these beams by means of the structural nodes, being theoretically the articulated nodes or joints, and uniformly distributed along the neutral axis of the beams. Outer force is transmitted via the short vertical member and by means of the intermediate system to the structural nodes. The intermediate system is built of two subsystems. The first one is called a funicular system, and it is located below the neutral axis, while the second one is called an arch system, and it is placed below the neutral axis of these beams. When pattern of the both subsystems are symmetrical towards the neutral axis, and when they are combined together, they create then only vertical components of reactions act in the boundary areas. The loads can be applied in various symmetrical, eccentrical ways. Nodes of the type C1 and C2 mustn't be connected to the mother of the main beams of the structure. The lenticular form of the intermediate system placed between these two nodes is considered as the modular unit of the foundation. It can be repeated many times along the horizontal direction. Number of replication of the lenticular units is optional, what implies that the horizontal surface of this foundation can be theoretically unlimited. This structural system of composite foundation can be a base for various shapes of the mega structures. I have proposed this system of foundation as a structural base in the conceptual design of a megastructure called the Geodome Sky Towers, prepared for one of the architectonic competitions. The towers are of the height equals around 380 meters. The support base has form of a square. Its edge length equals around 250 meters. The geodesic sphere has diameter equal to 100 meters. I have proposed again the system as the base structure of an artificial island in the conceptual design entitled Ocean Agave, prepared for another issue of series of the architectonic competitions. It is designed as a floating structure in subtropical ocean areas in the far distance from the land, being a settling unit that is self-sufficient in terms of energy and food supply, and be able to house a group of around 150 persons. The circular form platform of the Ocean Agave has slightly more than 400 meters. Spatial modules of this system of composite foundation can be made as a huge waterproof boxes having substantial uplift pressure. That is why they could be the component parts of an artificial island able to float on a lake or on a sea. Taking into consideration the basic rules of symmetry is also very helpful in the methods of static calculations. During my research stay at the Delft University of Technology, I have got a task to do an initial static analysis of one of the tension structures proposed in my doctoral thesis. Beforehand, I was required to do a physical model of it. The static scheme of the left-hand side of this slide shows a simplified cross-section of the structure, and it represents the fourfold statically indeterminate tension truss. When that system is overloaded, the four members of the top cord are slackened, what implies that they are excluded from the force transmission. Therefore, the scheme of the overloaded structure shown on the right side hand represents a statically determinate truss or system. Number of the excluded tension members equals 4, and it is equal to the statically indeterminacy of the basic truss system. This observation arises a following question. Is it possible to calculate in 2 stages such complex truss by help of method applied only for calculation of the statically determinate systems? Answer for the question is presented on this slide. In the first stage, one should remove a number of members equal to the statically indeterminacy from the top chord of the basic truss, what gives in the result the truss having scheme shown on in the central set of the schemes F diagrams. That form of the statically determinate truss has to be loaded by the forces having half values of the load forces applied to the basic truss. A very similar procedure has to be done in the second stage. In each stage, one can use, for instance, the Cremonez or the Ritter's method. Because these methods don't take into consideration the stiffness differences between members, that is why the just presented 2-stage method may give in the result only the approximate values of forces. The final values of these forces acting in members of the basic truss will be the resultants of values of forces detected in each stage in members having the counterpart positions in the statically determinate trusses. It is dictated by the principle of superposition and rules of the calculus of vectors. The differences between the false values calculated in the same truss members by the application of these two different methods are rather small. From comparative analysis of the results obtained in both the calculation methods, follows that the two-stage method can be applied as an approximate method of calculations of the statically indeterminate trusses. As I have previously pointed out, I apply fermion in all fields of my research and professional activity. I am still an aviation enthusiast, being a participant of series of special scientific conferences. I was encouraged to present a structural concept of an airplane, which I initially designed in my youth. The main purpose of the proposed structure was striving after getting an airplane having a large range of the flight speed, in particular of high cruising speed, by an airplane equipped with propulsion of relatively low power. In the next few slides, the structural concept of it is presented. You can notice that, in fact, only the nose of the airplane can be rotated. Now, being retired and having more free time than before, I plan to finish working out the new structural concepts of the airplanes. I believe they could be useful. Of course, they will be symmetrical, and for sure, I will apply fermion for defining numerical models of them. I hope that after this presentation, you can share, even partly, my opinion that the simple rules of symmetry, together with the principle of superposition, have always been very helpful in the fascinating process of shaping, design, and analysis of the spatial structures.